towers of K3 surfaces or something like this?
I will speak about towers of algebraic curves over finite fields. And families of K3 surfaces. Over finite fields as well. So let me start with motivation. Let C be a curve over finite field variance, and curve is smooth, projective, connected. And basic invariant of such a curve is the number of points in this curve. And well, what is known about this number? That there is a weight bound. That this number minus q minus 1 is not greater than 2g square root of q. This is called weight bound. Actually, that means that, well, this number is bounded like this, and we may ask, since the bound depends on g and of q, we may define the number which depends on g and q. This is the maximum number of points on any curve of genus G. How large is this number? How this number far from the bound? Is the question. For example, if q is not square, then this number is not integer. But well, we may use, in this case, we may use set bound. This is 2 square root of q. We take an integral part and multiply by g. This is set bound. And q. Number of points in the field.
But the second bound is stronger anyway, right?
That's right, but this one is older and more known. But well, this one is better. There is also an Hara bound and many other bounds.
So the difference between them is that
this is
in the first bound you can actually put the integral part just over all the
yes.
2q.
That's one. This is not straightforward to prove this bound from this one. You have something to prove here. Actually, this is a non-trivial result, really. This is a partial answer to this question gives the theorem due to Greenfield and Leditz. Let's take a limit. Let's take an arbitrary sequence of curves such that the genus tends to infinity. And in this case, the number of points divided by genus, this limit actually doesn't exist in general. Take upper limit. Yeah? In this case, this number is not greater than square root of q minus 1. So asymptotically, this is much better than 2 square root of q. Just maybe it's an exercise. If we divide both sides by g, take a limit, this limit vanishes, and we get 2g, 2 square root of q here. Greenfield and Webb says that actually the bound is much better. So when g tends to infinity, this number actually quite far from the bound as length. So next obvious question, can we find a sequence of curves such that this bound can be tended? And the answer is yes if q is square.
By the sequence, you mean covariance, yeah?
No, just the sequence, but of course, all examples are just, this is all towers, actually. I will define it right now. Maybe, okay, let me do it first. So all the examples actually that one usually constructs, actually it's an example of a tower. Tower curves. It's a sequence, infinite sequence of curves and finite maps. Well, such that this sequence is not trivial, so let me say that genius tends to infinity. So if q is square, actually there are many examples of this is called optimal tower. Maybe let me define it right now. If this limit if this limit is positive, then the tower is called good. And if the limit is equal to the Greenfield bound, then the tower is optimal. So let me finally say the theorem that if q is square, then optimal towers exist. This theorem is due to, I believe, Garcia Stichtinov. I believe that was the first example, but they constructed such a tower just explicitly, just more or less writing equations. This is called recursive tower. And which was more, then there were many examples due to Fassmann-Zink, for example, using modular towers, but they not, well, when you construct such examples in using modular curves of, for example, using elliptic curves or abelian varieties or some geometry, then usually you get optimal towers only for some q, say q is p square or something like that, or p to the 4. In general, Ihara obtained such a modular examples using Greenfield modular towers. So dream field appears again here. I believe he was surprised when that theorem appeared to have some connection to his construction of dream field modular curves. And the construction I will tell today, it's a kind of generalization of the modular construction. It was inspired by it. Okay, what's the idea of all these constructions? Let me sketch it. When we have a tower, suppose this is C1, and we have take one curve of this tower, Cm. How can we construct many points on? How can we find many points on Cm? Suppose we have a finite set T, finite set of points which are totally split. That means that all the points in the pre-image are also defined over Fq. So T is a subset of T0, C1 over Q. And the pre-image, say this is phi m. Okay. Totally split. So that means that the pre-image is also defined over the finite field. At the same time, if you look at the Riemann-Gurwitz formula, we can compute the genus of Cn from the genus of C1 and ramification. You will see that if we have too much ramification, then the part that ramification gives can spoil everything. So for this construction, we usually need that there are also a finite number of points on C1 such that all the ramification is concentrated over these points. So outside of this finite set, the tower is unramified. So that's the basic idea, how all these things are constructed.
Немного не понимаю, то есть мы сейчас живем, то есть вы сейчас показали картинку именно характеристики P. Значит, мы взяли там, то есть у нас там конечное множество точек. И мы сказали, что их прообраз будет всегда обязательно тоже, тоже набором каких-то точек, которые будут на нашем поле.
Because in general, that could happen that for an arbitrary morphism of two curves, that the pre-image of a Fq point is not defined over Fq. Because the field is not algebraically closed, but an exercise to find such an example. For a conic, say, conic goes to P1, yeah? Just a projection. Double cover. Double colorism. Yeah. Okay, so before I present the construction, let me just mention that in this modular construction U2 Ihara, this set of points, they were super singular points actually. So this construction, T is the set of supersingular points. And actually, in all modular construction, for example, if you take a modular tower for elliptic curves, you just compute number of supersingular curves on any modular curve. And this is enough for the bound. And today we will try to do this.
So T is the set of supersingular points, and C1 is, what is C1?
Well, C1 in a Harris construction, it's a Greenfield modular curve. It doesn't matter what is it actually, because
I'm trying to figure out what's a supersingular point. It's possible it's a point corresponding to.
For example,
curve.
in other constructions, when we talk about elliptic curves, we take supersingular points corresponding to, I mean, points corresponding to supersingular elliptic curves on the model.
So C1 and Cn are some kind of modular spaces.
Yes.
Like with different level structure.
Yes, sure. So Cn, yes, C1 is just the modular space without structure, and Cn
P1. P1.
Ты же просто говоришь, что это кривые.
Это кривые.
Ну, каждая из этих кривых сама по себе интерпретируется как процесс модулей некоторых кривых.
I don't explain this construction because it's kind of motivation and some.
Настя, послушай, здесь четко. Это пространство модулей чего? Elliptических кривых с какими-то дополнительными данными.
For example, but there are many more examples. And well, I mean, Greenfield modular tower, Greenfield modular varieties, sometimes they are one-dimensional, and they are used exactly one-dimensional. Okay. So the construction starts with a family of varieties of some dimension. So we have a base. We have a family with some base. In applications, U is one-dimensional, but actually this is not important so far. But maybe let fix it that U is open in some curve. Let us fix it. So let me just define that lambda n is the quotient link z to L to the n to z, where L is just some prime not equal to the characteristic. So if we have such a family, which is smooth, then the direct, actually any direct image, high direct image of F, high direct image of lambda n, well, there are many names for this, Lisse sheaf or anything you want. It's actually, it's a local system. Geometrically, this is represented by a one-dimensional scheme over U. I mean, it is one-dimensional, and there is a finite map to U. Since it is a local system, this is a union. In other way, we can say that this is a union of some open curves, actually, some open subset subsets and curves. Affine curves, but not over FP, but over some, actually, in general, over some extensions of FP. So the problem is here that this is our base U, and the local system is, well, the picture is actually the same, but this component could be reduced. There are many components. Some of them are trivial, and some of them could be reduced. So there are they're honest curves, but defined over some extension. So I would like to take a special family, special component in this local system, and I would like to prove that the sequence of these components will give me a tower, good tower or optimal tower, if I'm lucky. So my step 2 in the construction is to somehow understand that this this thing is not bad. Oh, sorry. This thing is more or less always bad. Yes, sorry. After step 2, this will be not the case.
So one-dimensional string over U, I think that's
Давай. Пусть домашнее задание делают. Ничего.
Okay, question.
okay. So the question was from myself, not from this guy.
Yeah.
By one-dimensional over U, you mean that it's a finite column over U, right?
Yes. It's one dimensional, and there is a finite
project.
multiple. What?
It's not project.
This guy
is open.
is affine.
Yes, and upstairs also.
Well, I was just puzzled by one-dimensional over U. Yeah.
Well, it's a curve, so it's easier to it is open subset inside in some projective curve. It's not a problem. So, well, the second step, the projectivization, is a different projectivization actually. So let me do it algebraically first. Let Mn be a free lambda n modulo. So it's lambda n is the string. This is the generalization of a construction of the projective space from the vector space. So let Mn star be Mn minus L Mn. So for n, when n is 1, this exactly means that we throw away 0 from the vector space. And the nth projectivization of Mn is the quotient of Mn star by lambda n star. So just usual projectivization when n is 1. When n is not 1, then we well, this is just something. There is an easy lemma that suppose there is a map from a module over lambda n plus 1 to a module over lambda n, such that well, its kernel is as small as you wish. So that it's fine. So the kernel is annihilated by L. Then there is a map on projectivizations. So an example of this thing is that we can apply this construction to this sheaf, because fiber-wise this sheaf is a lambda n module. So we can take a fiber-wise projectivization and get a, let me say this is Vn. So we get a sequence of one-dimensional schemes and maps between them, just as a corollary of this lamp. This is fiber-wise projectivization.
I don't understand. What is the statement of lemma?
Well, in general, if you have such a morphism between modules, there is no morphism from on the level of projectivizations. For example, if n is 1, you can take a zero map. You can always take a zero map, and then there will be no map on the projectivizations. So kernels should be small. That's the point. And well, this is well known that for direct images, this is the case. Well, they are not free, actually. It is important here that the model is free, but suppose for a moment that we are in such situation, these models are free, then we have a sequence, we get a sequence of maps. We would like to prove that there is a connected component in each of these one-dimensional schemes, which is first, it has to be defined over FQ. It has to have many points, and somehow we have to bound genes to get something like this. Maybe let me draw it like so. Here we have a connected component. I will denote un, and now we take a projectivization in the sense of curves. So we get a projective curves. But recall that in general, these curves are defined for some extension. So first, we would like to prove that under some condition, we can this curve is defined over FQ. Oh, sorry. Before I give this condition, one small remark. What is the fiber of Cn over C1, or actually Un over U? The geometric fiber. So the pre-image, so this is pi, no, this is pi m. So pi m minus 1 of some point A, where A is a geometric point on U. So this fiber over FQ bar is actually naturally identified with the usual type homology of the fiber of our family, which we started. In the same point A, and I will write this bar just to say that we take a fiber over the algebraic closure. So this set is finite, and the fiber is this.
Сейчас я правильно понимаю, значит, мы взяли сейчас какие уйты. Это какие-то множества просто в нашем...
Yes, I'm sorry. Projectivization of this thing.
И тем не менее, значит, уйты это просто какие-то множества в нашем PN, плюс 1 и PN, соответственно. А уйты кто такой?
It's a connected component. Because the picture is like this, there are many connected components, and some of them are trivial.
And how we construct C5?
It's
CN, and
just we have a one-dimensional scheme, and we take a projectivization in a geometric sense and get a projective curve, such that U is just open in C. So there will be an example how this works. I'm just explaining the general construction.
Why the fiber is this?
Sorry.
Why the fiber is this? I mean, P minus 1n.
Well,
This.
This is base change for a talc homology. I have such a local system. The fiber of this local system is exactly talc homology. Fiber of over some point. And then fiber-wise projectivization just gives exactly this. Okay, so now the condition. So let Y be some variety over Q, smooth, projective, and connected. Such a variety is called strongly supersingular. SSS. If Frobenius acts on the talc homology of Y, actually in any coefficient, say ZL, by multiplication.
Seriously, the only thing I don't understand why it is not a summand. I mean, because you take not all CN, but the component.
You're right. This is a subset.
A subset. Sorry.
This is a subset. You're right. So Frobenius acts by multiplication by just a scalar, and actually it follows from the Weil conjectures that the scalar is q to the power plus or minus I divided by 2. This in particular, that means that q is square or I is even. So this is possible only under this restrictions. So how this will help us? Here's the first proposition I will use. Actually, we get a stronger thing. So suppose there exists a point over of Q such that the fiber of our family over this point is strongly supersingular. Then this fiber splits completely. So it is defined over the finite field. In particular, there exists at least one point on Cn with coordinates in Fq, and in particular, this Cn is defined over Fq. So it's a curve over Fq. That's what we want. But at the same time, we get a stronger thing. Exactly what was used in previous constructions for good and optimal towers. Let me recall that we need at least some, but actually many fibers which split completely. Here we get exactly the same picture. And the proof of this proposition, let me just sketch it. Frobenius acts on this set. Actually, it's set since it is just scalar on the homology, on the projectivization, the action is just trivial. But this is actually exactly the definition of a point which is defined over Fq. Frobenius acts trivially on this point. So the proof is simple. So suppose we have a family, and we know that there are some strongly supersingular fibers in this family, but somehow we have to bound the genius of this curve, and actually we still have to find a huge connected component such that genius tends to infinity. So we need two bounds. Genius tends to infinity, and at the same time, actually for the limit, we need an upper bound for the genius. So a lower bound and an upper bound. So the slogan is that somehow we have to compute ramification. So computing ramification is the same as computing ramification in the tower is the same as computing monodromy of the family the original form.
Другой вопрос. Я правильно понимаю, что под ветвлением здесь мы подразумеваем то, что мы считаем, получается, каждое ветвление, то есть у нас же есть накрытие, вот это бесконечное последовательность, и там же на каждом уровне возникают точки ветвления, и мы их, получается, считаем все, да?
Надо все посчитать.
Ага, хорошо.
Yes, actually, it's thank you for reminding me. There is a nice sum that we have, as before, we have a second part of the picture. There is a finite set where f is not defined, or maybe f has degenerate fibers. And exactly over this finite set, we have some ramification. Maybe no ramification, but anyway, only over this finite set. So the picture is exactly the same as before. Okay. And actually, it is possible to compute ramification over FQ, but actually it is much easier to, if it is possible, to lift the family to characteristic 0 and to compute exactly the same thing, because monodromy is invariant. If the lifting is good enough, smooth, and so on, we can compute monodromy in characteristic 0, and the answer will be the same with the ramification and genus. This invariance, yes, they are invariant under lifting. So we lift everything to characteristic 0. I will write it, I will draw it. So suppose we have a lifting. So this is some u over z. And here's x. And also we have a fiber over C. Some W. Let me call it FC. And if this family is smooth as before, then it is enough to compute ramification here on the C fiber, and we get the same numbers as over finite field. So maybe we just want it. We will construct such a family.
Нет, ну вы же говорите то, что посчитать ветвление то же самое, что и подняться на замкнутое поле, там все посчитать, и все. Это то же самое. Правильно?
Да.
Почему? Просто я не понимаю, почему у нас количество точек ветвления не увеличится, когда мы будем подниматься на замкнутое поле.
So let me say it in a different way. Suppose we have a smooth family over U, which is, well, flat but not faithfully flat over Z. So it's one-dimensional a scheme of relative dimension 1 over Z, and the smooth family. And suppose that that P is not invertible in U, then we can take a base change, and we get the picture as before. At the same time, we can do a different base change. And well, I don't know how to explain it. Everything is flat or something like that. So this discrete invariants, they vary continuously. That's why they're constant. Okay. I think we don't need it. So now, well, I will use proposition 2. Suppose we have a point in outside of this W. Suppose the compactification of this W is some complex curve C. So Y is outside of W. So potentially it's a ramification point. And just fix any point inside W just because, well, we are talking about monodromy, fundamental groups, so we have to fix a point or in the fiber of this point, on the cohomology of this fiber, everything will act. That's why I prefix this A. So let My be the corresponding monodromy operator on each I. Actually, with coefficients in Q is enough for us. Oh, no, sorry. Lambda. Yeah. Then the fiber over Y, that F did I divide? Yes, I should say that we may apply the same construction for this map, for FC, and we also get a tower of complex curves. That would be Fn as before. Okay. So for this, the fiber of over Y for this curve Cn there is a bijection with orbits of My, or a group generated by My on this homology group, on the projectivization. Actually, as before, if we are talking about a connected component, then we have some subset here. Let me write the whole projectivization, but in general, we have some subset. I mean, here it is not important that Cn is connected. Actually, yeah, we just look at all ramification points, and connectedness is not important right now.
And I have a silly question. Is this subset obtained as the projectivization of a sum or of a subset in each I?
What subset? No,
This subset.
no.
No, it could be other.
Yes, we will see it in example. So example, just I will start it right now. Just let me explain what does it mean. It's actually an easy thing. So here's the point y. Here we have a. This is c. And over this we have a ramification point, something like this. The ramification point. So when we take a circle around y starting from a, then well, the picture is obvious, but that explains why we are talking about orbits of the action. At the same time, so this is just straightforward from the definition, but at the same time, now it's a question of linear algebra to compute such orbits, an operator x from some vector space. Okay, so now let me give an example of how this works. We computed this example jointly with Sergei Galkin. So I will start with a particular family of K3 surfaces, namely a deformation of Fermat quartet. So this is and this family is smooth over the spectrum. Well, we have to invert such lambdas where this family degenerates, and in fact, this is something like 2 lambda to the 4 minus 1. So exactly, I already erased it. So it's this is our curved U flat over Z. And for any p greater than 2, we can take a fiber of this family over finite field, and at the same time, we can take a complex family, which is actually well known for experts. And we will use it shortly.
So this is a kind of Hess family, but not for cubic curves, for K3 surfaces.
It's a family which appears in mirror duality between P3 and something which is mirror 2. So there is also an action of a group H, Z4 times given by, which I don't remember. So it's 0, 1, 4. There are 2 generators. The first one is 0, 1, 2 minus I. And here. Hopefully I'm correct here. Something like this. So we would like to apply the construction to this family, but actually it's a family of K3 surfaces. And we will take second cohomology. but well, this model is free, but it is of rank 22. This is too much. But H invariants, they are of rank 4, and this is much better. I will explain it shortly. But first, there is a nice theorem due to Sussman that if P is congruent to 3 modulo 4, then the fiber over 0 is 0. So exactly the Fermat quartic. Then this fiber is strongly supersingular over Fp squared. So we will construct the tower over Fp squared and assume that P is congruent to 3 modulo 4. So we know that our family has at least one strongly supersingular fiber. That's why we will get curves defined over Fq, and there will be enough points on them.
So it's like, there are less parameters in this construction than in the previous one.
Why?
But I think up to some point your field could be any FQ where Q is squared, and now you say that you are going to serve only the fields Fp squared.
Well, yes. Yes, maybe I should explain why we are doing all this. Yeah, sorry. Recall that for this strong supersingularity, we need that either Q is square or I is even. So there are already constructed optimal towers over squared Q. So it is natural to find. So for example, when Q is P, and we would like to find an optimal tower using this construction for Q when Q is P. We have to work with second cohomology or even cohomology. Unfortunately, I wasn't able to produce a tower over Fp anyway. But this example just shows that it is possible to compute something with second cohomology and to construct towers at least over Fp square as before. But using this new construction. So maybe if we will be more lucky and we will find a better family, maybe a more complicated family, then we will be able to find at least good tower over Fp using arguments like this. But so far I'm unable to do it, but here is an example that in principle this is possible.
So at the moment, over Fp, there are no optimal towers at all.
Yes, that's the point. And probably some say that actually they don't believe there exists optimal tower over Fp.
Do there exist good towers?
Yes.
They are known.
They are known.
And what would you need from the family to be able to construct at least a good tower from this family?
Well, actually, that's the point that I'm not focusing on this strongly supersingular condition because actually there are no strongly supersingular K3 surfaces over Fp. This is due to Artin. And I believe I can prove that actually there are no at all strongly supersingular surfaces over Fp of any kind. But over Fp, just over Fp.
And what about
so it is not possible that I think this is possible to prove, yes. So that, so this, I mean, this stronger super singularity, this is too strong.
I mean,
condition.
so you said that Artem tells us
Also,
that
Artem
there are no
proved that if a K3 surface is defined over Fp, then it is not possible that Frobenius is just multiplication by P or minus P on the second language.
So okay, and what's and you suspect that it's also not possible that the surface is super singular?
No, I suspect that this is also true for any surface.
Any as opposed to
Any surface over Fp. Not K3 surface, but just any surface. Yes.
And what about
actually, yes, we can do this example, and then I realized that possibly this is the case. So
what about FQ, for instance?
Probably the same story. I don't know. So let me just explain that we can construct towers using this all this stuff, but it's a sad remark that this strong super singularity, this condition is too strong, and we have to find something weaker, but at the same time somehow we have to get same corollaries as we get from this super singularity condition for a file. That's why I don't want to speak much about this condition, because right now it is not that interesting for me. Just super singularity, what is needed, but super singularity, just super singularity is too weak. So we need something in between. I don't know. Okay, so how can we construct compute ramification? Now we just tensor everything by C and use theory, which is actually all the computation was done for the purposes of mirror symmetry for K3 surfaces of the C. So, in particular, Dolgachev and let me say it correctly. So the results will be by Dolgachev, Batarev, Kotz, Korti, Galkin, Kasprzyk, Kasprzyk. Thank you. I'm sorry, Kasprzyk. This is yeah. So let me formulate it. So let me return to this H invariance. H invariance on the cohomology, they correspond actually to the quotient by this with H. So let V lambda be the discretization. I will tensor everything by C and use the same letters as before. Desingularization. And now the theorem is due Dolgachev, I believe. So V lambda is isomorphic to the family of Kummer surfaces. associated to the product of two elliptic curves such that there exists two isogeny So the data is a curve, a second curve, and the two isogeny. So the global monodromy group is very explicit. This is called Fouquet group of level 2. So it's a group generated by a matrix 0, 1 over square root of 2 minus 1 over square root of 2, and gamma 0 of 2. This is inside L2R. So we have an explicit group. Actually, we know how this group acts on this lattice. Maybe right now I will say something like this. Maybe it's better. And here we have a lattice T of rank 3, which is orthogonal to on the level of this family, we get an orthogonal to exceptional divisors and hyperplane section as well.
So, and in this picture, E1, for instance, so this E1 and E2, they also vary in one-dimensional family. They're not constant.
Yes, it's a family of converse surfaces. Actually, it's a modular family of converse surfaces. It's some base change actually of x0, 2. So it's a usual modular family of level 2. Something like that. So actually, we are still not far from the case of elliptic modular tower, but we can do, let me say just once more, that's the explanation. We can do such computations, and actually it's an easy computation, in fact, for surfaces. As Galkin explains me, there are, well, for many varieties, I mean, the varieties they are considering in this mirror story, they computed all this stuff, and ramification, monodromy groups, and all this. There is a big machinery for that. And actually, it is easy to produce much more examples of that sort. But all of them will be over FP squared. This is still a good question, how to produce something over FP, maybe starting from examples like that. Okay. Yeah, so let me return to this T. Since it's a sublattice in the second cohomology, there is a symmetric form here, and we can take a subset Dm is a subset of isotropic vectors. So when we take projectivization, let me write it like this. So this is Actually, it's a cone over a conic. So when n is 1, this is just P2. P2, and there is a conic inside. And this is the fiber of our connected component, actually. So the connected component is not a direct sum. It's basically like a conic in P2 in J. So, and actually this is the big difficulty. But I believe I don't have time to go in such deep things. Okay. So first, this is the conic. In particular, let's compute something at least. There are exactly L+1 points on this conic. And at the same time, this is obvious, but for others, for somebody this is obvious, for others this is a nice exercise, that this map, which is induced.
Do you mean U and Golden?
Okay, this is a nice exercise on all this stuff. That just look at the projectivization. Rank of T is 3, and we take such a map. Then the fiber is of ordinarity L squared. But since this thing is of dimension 1, then the degree of the restriction of this map to this conics is actually L. So we know the degree of our map. Let me just say that, okay, we started from the family of K3 surfaces, so we obtained in this way a family of a tower of curves, and we know that the degrees are just L all the time. And on the first curve, there are L+1 points. Maybe it's better to say it. No, I'm not. There is a map to C0, and this last map is of degree L+1. C0 is our base, just P1. Okay, what about ramification? That was computed by Coates, Galkin, and other guy. Sorry, I'm unable to pronounce his name.
No, Sergej is not pointing to somebody in the room.
He's not here.
That's Polish. Yes, I'm really sorry.
He also doesn't mean our third organizer.
Yes. Kasmich. Yeah. So there are 5 degenerate fibers.
So what's written there?
5 degenerate fibers. And here comes mirror symmetry because we compute degenerate fibers for V lambda. maybe that's the strange point. But since we this is easier and this is enough, because we are looking at the part of cohomology which is the same for x lambda and for the measured dual. So this is not important to which family we compute the ramification of the monodrome. And it turns out that the monodrome is computed for the measured family, and this is enough for us. So we are talking about the mirror family. So it's a quotient. This. And by the way, we know the global monodromy, and that's why I didn't mention it, that this T is invariant under the global monodromy group. Of course, the isotropic vectors are also invariant. And it's a straightforward calculation to show that actually this group acts transitively on the set. That's why actually this dm corresponds to a connected component. The argument is the same as with that proposition 2, that the orbit corresponds to a connected component. So 5 fibers, infinity, and plus minus 1, plus minus I. So they correspond to some, these 5 points correspond to 5 ramification points. Let me define, just denote ramification R infinity and R. These are just the sum of all ramifications for these 4 points, because they're similar. So here we have, actually it is not important what happens here. We just bound the ramification by the degree, and we already computed that the degree is, maybe let me write it, ramification of the level n, yes, is bounded by L plus 1 times L n minus 1. And here the monodromy operator is just local monodromy operator. This is a hyperplane involution, just involution. And when you restrict an involution to such a set, you get actually not more than so there are 4 points, and for each point we have not more than L plus 1 times L n minus 1 divided by 2 orbits of degree 2. So we have to compute how hyperplane involution acts on, say, on a conic, and compute the number of orbits of degree 2. It's a nice exercise on plane geometry. So we get such a bound, and now just apply Riemann-Hurwitz, and it follows that the genus is bounded by L plus 1 times L n minus 1 divided by 2, and probably plus 1. At the same time, we have one split point in this tower, and that's why the number of points on CM over P square, this is at least L plus 1, this is at least degree. So altogether, the limit of this quotient is greater or equal to 2. And actually that means that, recall that P is congruent to 3 modulo 4. For general P of this sort, we get a good tower, but if P is 3, then the tower is optimal. Actually, if we were more careful, then it would be, I think it's not hard to prove that this tower is also optimal for many P. But as I mentioned earlier, strongest supersingularity is too strong for us, and since we are not able to produce a tower over P, we just didn't want to make this computation more, more careful, to prove a better bound.
So you actually don't produce an optimal tower. You produce an optimal tower only for the field of 9 elements.
Yes, let me explain. What does it mean, optimal? So we have to get square root of q minus 1, but q is 9. So square root of 9 minus 1. This is exactly 2. Yeah.
So your tower is optimal only over one field.
Yeah.
9. And once again, so
I just said that possibly this is optimal over all these fields, but you just have to compute this. Have to understand that you have more strongly supersingular fibers. And this is fine.
So this computation is still not enough?
Yeah, I think you can do better even for this example, but this is not important. This is just an example of computation that you can do things in that way. Actually, the goal is to produce a tower over Fp, and so over Fp squared is not that important to produce many strongly supersingular fibers. Okay, I think that's all. Thank you.
Any questions? I think I have a couple of questions. So first, so you said that some people believe that there are no optimal towers over P, and how do they support the expectation? Well, maybe,
well, for example, if q is not square, then this square root of q minus 1 is not an integer.
That's very interesting remark.
But usually in all the examples you can construct, even just good towers but not optimal, this limit is rational. So it's not even in Q. Yeah. But at the same time, probably there is a better bound, but it is still not be proved that there is a bound like this. Or maybe something like this. There is no bound of this sort. But possibly this is the case. And that's why. So the expectation that actually we have a bound of this sort, an integer or even an irrational, at least rational number. No, this is true. I mean, so maybe not integer, but a rational number. But well, Greenfield is not interested in this story so far, and that's why we still don't have a better bound.
And also one more question about the very basics. Can you comment once again about the definition of supersingular and the theorem of Artin? So by definition, a variety is supersingular if the Frobenius acts on every homology group by a scalar.
No, that's strongly supersingular. Supersingular means that that's the, well, for K3 surfaces, that means that the rank of Miron-Severi group is 22, for example. Well, in our case, in general case, the definition is that we have the characteristic polynomial. Actually, it's better to usually so characteristic polynomial, we have eigenvalues of Frobenius, so that pi eigenvalue of Frobenius, and for any such pi, well, this is known that its complex norm pi is q to the I divided by 2. So for supersingularity, we have something similar, but for periodic norm. In general, this is not the case, but if we have it,
Как это связано с группой Miron-Severi?
it's a nice theorem that for K3 surfaces, from this we get that the Miron-Severi group over this story is over the algebraic closure, or at least over a large field. This multiplied by UA is isomorphic to H2. And actually, over C, usually this is not the case. It is not possible when you multiply Miron-Severi by Q and get an isomorphism.
So what does Artin theorem tell us once again? It tells us that over of P, there are no singular or supersingular or strongly supersingular.
For supersingular.
No supersingular, guys.
No, I mean, if you have a supersingular surface, then the Frobenius action on this guy or on this guy is not scalar. So modulo, well, it could be multiplication by P or minus P, but this is not possible. You always have plus P or and minus P as eigenvalues.
So this is the theorem of Artin.
Yes.
So no strongly supersingular K3 surfaces.
Well, it's a reformulation.
Yeah, okay, it's equivalent.
It follows from his result. His result is
and roughly what's
about Brouwer groups.
What is his about Brouwer groups?
Yeah.
And in general, suppose that you have a strongly supersingular surface, then in the definition of strongly supersingular, you require that on every homology group the action is scalar, or just on the second homology group?
I used only one number for.
For K3, it makes no difference because you don't.
Yeah, for K3 it's just 2, but actually it's better to say strongly supersingular in dimension, say I, in dimension, some dimension. But
over of P, it doesn't make much sense to consider strongly supersingular in rank 1, right?
Sure. Yeah. In rank because of this. Yeah.
And so you said that you expect there are no strongly supersingular surfaces at all, not just K3 surfaces over of P. So
yes.
What do you mean by this? So that K3 are served by K3 surfaces are served by Artin. Then is this property preserved by contracting a minus one curve, for instance?
What?
Suppose that you have a surface which is strongly supersingular, or maybe not strongly supersingular,
yeah.
And you have a minus one curve on this surface. Is this property preserved after contraction of such a curve?
Sure. just because, well, this is an invariant element in the neuron severity. We are talking about eigenvalues. You have an eigenvalue, you have your set of eigenvalues, and this exceptional line generates a subspace of dimension 1.
Класс ваш 2.
Yeah. When you blow it down, you just erase this, make a quotient by this class.
Yeah, but
And
will
still you have the same set of eigenvalues, and if the action was scalar, then it is still scalar.
yeah, wait. So if it was scalar, it's still scalar, and but if it was not scalar, can it become scalar? I suppose you had p and minus p.
Но у тебя есть отображение между когомологиями, которые
Yeah,
согласуются с пробелом.
no. He's talking about a different thing. Well, that means that if all the eigenvalues was minus p and you have 1 plus p, and this plus p just, of course, this corresponds to an invariant, Frobenius invariant exceptional person. If you blow it down, then you will get a stronger supersingular surface. But it is not possible to construct such a thing.
So which surfaces are difficult from this point of view? So you have for abelian surfaces this. Okay, let's restrict to strong supersingular dimension in rank 2 for second homology. What do you know about this property for other surfaces, like abelian surfaces or general type or rational?
For abelian surfaces, we just have a classification of characteristic polynomials, and so it's easy.
So and there are no
strong supersingular. I believe it is possible to prove that it is not possible for. There are no strongly supersingular surfaces over Fp, but last time I tried to prove it, I found a gap in the proof, and but well, I believe it's possible.
But in principle, do you like when you prove it? Okay, modular gap. Do you use classification of new models?
No. I just it's a variant of Hodge theory in characteristic P. So we have an analog of Hodge filtration, so maybe like some filtrations corresponding to Frobenius, and just playing with this filtration, I think it's possible to prove. So the idea is that actually modulo P, if you take a periodic homology and take everything modulo P, you just have a Hodge filtration, and this filtration is non-trivial, and it forces Frobenius to well, it's a long story. Can't say it shortly. It's a long story.
But you very interesting figure, even modular gap.
Yeah, that's right. That
Okay,
would be
other questions? If no, let's thank Sergey again.